Hello everyone. So this is a question from JEE Mains 2026 8th April Shift 2. Given below are two statements. Okay, so they have given us the value of R and also 1 calorie is 4.2 joules. Statement 1. When activation energy is 12.6 kilocalories per mole, the room temperature rate constant is doubled by a 10 degrees Celsius increase in temperature from 298 to 308 Kelvin. Okay. And statement 2 is for a first order reaction from A to B, a graph is given between T half and the initial concentration. Okay, and this is the graph that is given to us where, okay, A naught is the initial concentration and T half is the half line. So they're asking us, which statement is correct. Statement, whether, statement 1 is correct or true or false, statement 2 is true or false. Okay, so the chapters involved is chemical kinetics. Okay. So let's look at statement 1 properly. So when activation energy is this much, room temperature rate constant K is doubled by a 10 degrees Celsius increase in temperature. Okay. So the effect of temperature on the reaction, or you can say on the rate constant, because rate of a reaction is determined by the rate constant, because we know that rate is directly proportional to rate constant into concentration of reactants to the power the order, right? So when we say rate of reaction, we imply rate constant, right? So the effect of temperature on the rate of reaction, or you can say the rate constant, is expressed in terms of a quantity called temperature coefficient. Okay, so there is a term called temperature coefficient. So this guy is having a symbol N. So the formula or the value of temperature coefficient is rate constant at T plus 10 degree and divided by rate constant at T degree. So in our question, they have given us temperature is increased from 298 to a 10 degree increase to 308. So this will be actually 298 Kelvin and this will be actually 308 Kelvin, right? So what is temperature coefficient? Temperature coefficient is the ratio of rate constant. We can also write it as K of the reaction at T plus 10 degree divided by K of the reaction at T degree. So this value for most of the reactions, that is the value of temperature coefficient for most of the reaction, is between 2 and 3. Okay, so this is because we know that, so there is a reason behind this, why it is almost the double. Why is the rate constant at T plus 10 is almost twice the rate constant at T. So there is a reason behind it. So we know that for a collision between molecules to be effective, the colliding molecules must have energy more than threshold energy, right? That's why if you remember the curve, we have to apply, let's say this is the energy of reactants. So we have to give some energy to these reactants, only then the barrier will be passed, right? So this, the energy that you have to give to the reactants, this energy is known as the threshold energy. And this is known as the activation energy, right? So every molecule should have energy more than the threshold, or you can say the colliding molecules must have energy more than the threshold. This is the threshold energy, right? So the fraction of molecules having a particular kinetic energy at a particular temperature remains constant. Okay, so I will write that important point. First is, colliding molecules must have energy more than threshold energy. What is threshold energy? I will draw a diagram. So this is the energy of reactants, average energy of reactants. This is the average energy of products. This is the threshold energy. And the difference between threshold energy and energy of the reactant is known as activation energy. Okay, so everyone should have energy more than this much. We have to cross this barrier, right? So therefore this statement is true, that colliding molecules must have energy more than threshold energy, right? And the next statement is also equally important, that fraction of molecules having a particular kinetic energy at a particular temperature remains constant. Okay, so if we draw a graph between, you know, fraction of molecules versus kinetic energy, we will get a curve like this. So we will get something like this, right? This is, let's say, at a temperature T. So what I'm trying to say is fraction of molecules having a particular kinetic energy. So let's say, you know, this is a fraction of molecule having a kinetic energy this much at temperature T. So this whole curve is for temperature T. So that is constant. For example, this much fraction will be having this much energy. This is constant. This won't change at the same temperature. Okay, cool. So now I will, you know, and let us say this is the threshold kinetic energy. So let's say this A is the threshold kinetic energy, and let's say the graph, you know, ends at this particular point. So this will be B. So A, B, C, D. So this shaded area, that is A, B, C, D, this region, A, B, C, D, this is the fraction of molecules having energy more than threshold energy at this particular temperature T, isn't it? Because this fraction will have energy more than threshold, that is A. This fraction will have more than threshold A. So this fraction has kinetic energy more than the threshold energy at that particular temperature, right? Now, when we increase the temperature to T plus 10, so this was, don't forget, this graph is for temperature T. When we increase the temperature to T plus 10, why are we doing that? Because we want to see what happens to the rate constant, or, you know, the rate to the rate of reaction at T plus 10 compared to what happens to the rate constant at T. So we see something very interesting. Now the curve will shift forward and also decrease in height. So this is what it looks like. So this is what it looks like now approximately. So now, and this is, you know, at temperature T plus 10. So therefore now you can see the curve shifts to right. Now the fraction of molecules having kinetic energy more than threshold is this. So I will draw the, so you can see this at T plus 10, this is the fraction of molecules having, you know, energy more than K, or the threshold energy. And that region is represented by A, B, E, F. So at T plus 10, this is the fraction of molecules having kinetic energy more than threshold. At T, A, B, C, D is the fraction of molecules having kinetic energy more than threshold energy, right? And the area under, I mean, area of ABEF is almost double of area of ABCD. So that's why you can see the fraction of molecules at T plus 10 having energy more than threshold is double to the fraction of molecules having energy more than A at T. So therefore, the N value, the temperature coefficient, is approximately between 2 and 3, or, you know, the double. So this is, you know, qualitatively. Quantitatively also we can say, or we can calculate. So we know that, so quantitatively we know that K is equal to AE to the power minus EA by RT, right? Where, you know, this K is the rate constant, A is the pre-exponential factor, it's a constant for a particular reaction, right? E is the log base E, I mean, it's Euler's number. EA is activation energy, which is again a characteristic of the reaction. R is the gas constant, T is the temperature. So this is also known as the Arrhenius equation, right? So when we take log of both sides, so it will become ln K is equal to ln A minus EA by RT. So let us say that at temperature T1, the rate constant is K1, and at temperature T2, the rate constant is K2, right? So therefore rewriting these equations, so it will become ln K1 is equal to ln A minus EA by RT1. For temperature T2, it will become ln K2 is equal to ln A minus EA by RT2, right? So let us say this is equation 1, this is equation 2. So if we subtract 1 from 2, that is if we do 2 minus 1, so we will get ln K2 minus ln K1 equal to EA by RT1 minus EA by RT2. Or you can write ln K2 by K1 is equal to EA by R1 by T1 minus 1 by T2. In the question, they have given us that the activation energy is 12.6 kilocalories. So we can write it is 12.6 into 1000, and also 1 calorie is equal to 4.2, and R value is 8.314. Okay, and the initial temperature is 298, final temperature is 308. So this will give us ln K2 by K1. So when you do this calculation, you will get this value as 0.693 approximately. So we get this value approximately as 0.693, and we know that 0.693 is, ln2. So therefore K2 by K1 is nothing but approximately 2, or you can say K2 is 2 times of K1, or you can say the rate constant at 308 is double of the rate constant at 298. So this is, qualitatively. Using formula we got this, right? But it's an important fact that you should know that for every 10-degree increase in the temperature, the rate constant doubles up, or you can say the rate becomes double. Okay, that is because of this, Maxwell's distribution curve, that is qualitatively, and this we have calculated, that is quantitatively. So I would suggest you to remember this as a fact. Okay, so therefore statement 1, what is it saying? Statement 1 is saying that when EA is equal to itna kilocalories per mole, the room temperature rate constant is doubled by a 10 °C increase in temperature. So this is a correct statement. So statement 1 is true. Okay, statement 2, for a first order reaction from A to B, so this is the curve T half versus A naught. Okay, so here what is important, that they're talking about a first order reaction and they are drawing a graph between T half and A naught. Okay, so let us try to find a relation between them. So we know that the reaction given to us is A to B. So this is for statement 2, and it's given that it's first order. So obviously minus dA by dt will be the rate of the reaction. It will be directly proportional to concentration of A to the power 1, since it is first order, right? And order is the power, sum of the exponents. So you can write minus dA by dt is equal to K into concentration of A, and you can write dA by concentration of A is equal to minus K into dt. Integrate both sides, limits of integration A naught to A, 0 to T. So this will become ln of A minus ln of A naught. This will be minus K into T, right? So you can write ln of A by A naught is equal to minus KT, or you can, take the reciprocal, ln of A naught by A is equal to KT. So this is the final equation, right? We know that T half, or, at half-life, at T equal to T half, the initial concentration, the concentration at that point at, half-life is half of the initial concentration. That is, concentration of at A is half of the initial concentration, right? So substituting these values in this equation, we get ln of A naught divided by A naught by 2 is equal to K into T half, right? So we get ln 2 is equal to T half, and ln 2 by K is equal to T half. So you can see T half is, ln 2 is 0.693 by K. So you can see T half is independent of the initial concentration A naught. There is no A naught term in this equation. So therefore the curve between T half and K should actually look like this. T half and the initial concentration A naught. It will look something like this, because T half doesn't depend upon A naught at all. So the constant value of T half will be maintained irrespective of what is A naught, right? So, but in our question, in statement 2, they have given us that the relation between T half and A naught is like this. So this shows that there is direct proportionality between T half and A naught, which is not correct, right? So therefore statement 2 is incorrect. This should be the actual curve between T half and A naught. So therefore statement 2 is incorrect, okay? So statement 2 is, this is false. Instead it should look something like this. Okay, so therefore the correct answer will be statement 1 is true and statement 2 is false. Okay, thank you.